Comes on everyone. Let's start off. Great. So last thing that we did was we are doing parallel plate capacitors. Great. Now let's go ahead with one more question. So if you see in the last class, right, the whole story was this, that electric field lines are kind of a form of energy. So if you have more electric field in the region, you have more energy. So we got something called energy density, which was half epsilon E square, which is energy per unit volume. So using that as a concept, let's do something. Let's say we have a charged hollow sphere, which has a charge plus Q. Now, because the shell is having a charge, it will have a lot of field lines. And like we discussed, if there are field lines, there is energy. So find the ratio of energy stored from x is equal to r to x is equal to 2r and x is equal to 2r to x is equal to infinity. Meaning, just to give a little more context, see, you have a shell. If you look at the field lines, you have a field lines going from here to infinity. Now, we said the field lines are nothing but energy. So I'm asking you, if you take a shell from R to 2R, so this is R, this is 2R. So in this green color region, there is some energy. How much is that? And then all the region outside this green, how much is that energy? I want that ratio. Is that making sense? So that means when you say the energy of a shell is something, that energy is not inside the shell, it is not on the shell, it is actually in the space. That energy is distributed in the entire space in the form of field lines. How do we do this? X is the distance from center. We have to use energy density formula. Energy per unit volume is half epsilon E square. Let's see how will you handle that. Think for a minute or two. These are some good questions, based on this energy density. Means if they give you field in a region, you can actually figure out the energy stored in that region. Others do keep your cams on. So how do we go about this? Okay, let me write Arya. Samyak ne. That's not the answer. Now see, I'll show you something. So let's say at a distance x, consider a thin shell. Whose thickness is dx. Now in the formula, d energy by dv, that's your energy density, is half epsilon E square. So the energy in the region is half epsilon. What is the field there? Field will be k q by r square. In this case, k q by x square. That is your field k square. Into volume will be what? Volume of the shell, which is 4 pi x square into dx. This is the volume of the thin shell. So this much energy is there in the thin shell. This is the field, right? Now, just to suppose if I calculate the total energy, means if I want to say all the energy in the space, remember the field inside the shell is anyway zero. That means there is no energy inside that hollow space. Whatever energy was there, it is always outside only. Yeah, so you have to, so total energy will be integral. So the energy is from where to where? Energy is from R to infinity. I didn't ask you this, right? But I want to show you something. Now, if you integrate this, this would be half epsilon. K is 1 by 4 pi epsilon. So that would be 1 by 4 square, 16 pi square, epsilon square, q square by x power 4, 4 pi x square dx. You solve this, you integrate this, you end up with an answer. So that 4, 16 will cancel. That is 4, that will get 8. 1 4 pi epsilon will cancel. You'll get q square by 8 pi epsilon. That would be dx by x square from r to infinity. This will be like 1 by r. So you'll get k q square by 2r. Anyone remember what is this? This is your self energy, isn't it? This is the self energy of a hollow shell. So this term, what we got is the self energy, which we derived in electrostatics. So that means, when we are saying the self energy of a hollow shell is kq square by 2r, so where was this energy actually stored? This energy was there from the surface to the infinity. The energy was not inside the shell. It is not on the shell. It is in the space. Are you clear with this? Do you guys remember this self energy of a hollow shell? Got it. So this will give you the total energy. Now, what you're asking, you want only the ratio, right? So you want energy from x is equal to r to x is equal to 2r. Energy from x is equal to 2r to x is equal to infinity. So it is simply integral. So this formula there, q square by 8 pi epsilon r, integral dx by x square. Limits will go from r to 2r. So you can even find energy in the space, like you can find the total, or you can find even in some particular regions. So the whole integration will remain same, only the limits will change, 2r to infinity. When you do this, interesting, you'll get 1 is to 1. Means see, all the energy that you have from r to 2r is equal to all the energy you have from 2r to infinity. So the closer you are to the shell, the more energy you have close by. Obviously, more field, so more energy. Is this ratio clear, everyone? How we got this? Any doubts on this? This is a pretty good one based on the self energy. So this can be called as self energy. This is also the energy stored. So they should be the same thing. Any doubts on this? Clear? It's a good one. Now, based on this, if I ask you a similar question, let's call it B part. Let's say we have a uniformly charged solid sphere. This is plus q and radius r. Find the ratio of energy inside the sphere and outside the sphere. Can you do this without doing any integration? Find the ratio of energy inside the sphere. So when I say inside, it is from x is equal to 0 to x is equal to r, and outside from x is equal to r to x is equal to 2r. Yeah, one way to do is do integration. Like, you know the field inside, you know the field outside, substitute karo, solve karo, you'll get an answer. You can do this without any integration, without anything in a minute. Think from that. I know you can handle integration. So integration में सिर्फ क्या difference आएगा? This part which is there, half epsilon e square, this will become k q x by r cube for inside, isn't it? That will change the field inside, and the field outside will be k cube x square. So that is fine. You can do with calculus. Can you do this without any calculus? Think, how can you do without any integration, nothing? Think for a minute. That's a very good way to think. Give you a hint. Let me tell you this thing. Listen, if you take a solid sphere or a hollow sphere, the field outside is same. Do you guys agree with that? What is the field outside a hollow sphere? KQ by R square. What is the field outside a solid sphere? KQ by R square. That means the field outside is same. If the field outside is same, then won't the energy outside same? Does the system know who is creating that field? As long as the field is same, the outside energy is same. That means the self energy of a hollow sphere is the energy outside the solid sphere. Is that logic making sense? And do you know the self energy for a solid sphere? You know the self energy for a solid sphere. There is a total energy inside and outside. You already know the outside energy. Subtract it, that will give you the inside energy. If you understood what I said. So you can get this without any integration if you use that logic. The worst thing, you can just put the formula and integrate. But think about what I said. Take a minute more. Let's see if you can get an answer. Since the field outside the solid and hollow sphere is same, the self energy of a hollow sphere, which is kq square by 2r, must be the energy outside the solid sphere. And you know the total energy for a solid sphere. So from total, if you subtract the outside, jo bach jayega, that must be the inside energy. I hope that argument is making sense. Okay, let's see. So the total energy is, if you guys remember the formula, 3kq square by 5r. Remember this? This is the self energy of a solid sphere. You should remember your results. And then we are going to argue, since the field outside is similar to field outside a hollow shell, the energy must be same. So energy outside, that is from x is equal to r to x is equal to infinity, must be kq square by 2r. From this argument, the energy inside, which is from x is equal to 0 to x is equal to r, must be the total energy, E total minus E outside. If you subtract this, you'll get 3 by 5 minus 1 by 2. How much is that? 3 by 5 minus 1 by 2, 3 to 6. 6 minus 5, 1 by 10. The kq square by 10r. And you're asking the ratio of this. So kq square by 10r and kq square by 2r. That's 1:5. Is that making sense? This is energy inside by energy outside. There's you literally with that logic you can skip all that integration and get an answer. Yeah, but again, exam में कभी कभी click नहीं होते हैं. That is okay. I mean, you know how to do it. Take a shell of 4 pi x square dx, find the field, integrate. Little brute force. It'll take a minute more, but you could have got it. All clear with this. This is one another interesting way of finding self energy of a system. If someone gives you a system and they ask you find energy, you can do this. Now, if you want to do a little more practice on this, you can try this. I will leave it as a homework. You can try this and check. If you have a solid cylinder, infinite solid cylinder, uniformly charged. Rho is the charge density. Find the energy inside and outside ka ratio. Volume, charge density. So for first, you need to know the field inside. How did you get the field? We get it from Gauss law. You can try this as a homework. Like this is how they'll play around. There is no way to get energy other than the rough epsilon E square. Find the ratio of energy inside and outside. You can try this as a homework. I don't know the answers. If you got something, let me know. Field, if you don't know, go to Gauss law. We did field there. So get the field there and integrate and you'll get the answer. All clear with this? So this is one way of playing around with these questions. Any doubt so far? Anything you're not convinced of, please ask me. So self-energy, energy density, you can relate them both. Clear? Next thing. So that's your parallel plate capacitor. The next thing is your spherical capacitor. So in a parallel plate capacitor, we have two plates facing each other. In a spherical capacitor, we have two shells. So spherical capacitor is constructed by concentric shells. Others do keep your cams on. So consider we have two shells. Radius is R1 and radius is R2. Let's say you connect a battery between the inner and the outer shell. So this is the battery V. Now, because of this battery, you will get some charge plus Q, you will get some minus Q. Then, the field between the plates E is given by KQ by small r square. So R is between R2 and R1. This is the field between the plates. Then we know from electrostatics, the potential difference V plus minus V minus is integral E dot dr, which is KQ square by R square dr. Limits will go from plus means that is upper limit, which is R1, minus is your lower limit, R2. Integrate this. This would be KQ, 1 by R1 minus 1 by R2. V plus minus V minus is nothing but your potential difference. This would be Q by 4 pi epsilon. 1 by R1 by 1 by R2. And if you guys remember the definition of capacitance is nothing but charge by voltage. So if you take this ratio, you end up with 4 pi epsilon by 1 by R1 minus 1 by R2. There, this is a formula for capacitance of a spherical capacitor. Exams like, CET, bits, this would be a direct question. They'll give you two capacitance and say, what is a capacitance? So parallel plates ke liye, what is the formula? A epsilon by D. For spherical capacitor, the formula 4 pi epsilon, 1 by R1 minus 1 by R2. I'll put it in a better form, but please have a look at the derivations. Clear what we did? So we kept a battery, we got a charge. If you see, we did the same story for parallel plates also. Parallel plates mein we did similar. I said there was a battery, then I said we got a field, then I said field into distance is potential difference, then I got Q by V. So this is what I was saying. The capacitance does not depend on charge or voltage. It depends on the material. It depends on the shape of the plates and everything. So for parallel plates, it depended on an A epsilon by D. For spherical, it depended on R1 and R2. So let me put it down in a more usable form. So when you take two shells, this is R1 and this is R2. Can someone tell me when you say spherical capacitor, where is the capacitor exactly here? Where is the capacitor here? Is the capacitor the shell? Outside the shell? Inside the shell? Where is the capacitor exactly? Between the shells, right? If you see when this was plus Q and this was minus Q, how are the field lines? The field lines are going from here to here. The space between the capacitors, the shells, is the capacitor. The shells are not the capacitor. Space between shells is the capacitor. The formula is given by 4 pi epsilon 1 by R1 by 1 by R2. If you can simplify this, you end up with 4 pi epsilon R1 R2 by R2 minus R1. There. And you want to find energy stored, all the formulas are valid. Energy stored is what? Q square by 2C. You can put that Q or half CV square, it will work. Whether it is a parallel plate capacitor or a spherical capacitor, the Sika value, you really can't tell a difference. If I say capacitance is 1 farad, you can't tell whether it is a parallel plate or a spherical plate. So now here there is a case. If R2 tends to infinity, look at this thing. This is another interesting thing. If R2 is infinity, that means there is no outer shell. We get a single shell. So this is a single shell capacitor. So where is the second shell here? The second shell is at infinity. So all the space from the surface to infinity is the capacitor. So you can even have a capacitor like this. Even a single shell can be treated as a capacitor. Now look at the formula. What happens? If R2 is infinity, then 1 by R is 0. You end up with 4 pi epsilon by 1 by R by 1 by infinity. You get 4 pi epsilon R. This is your single shell capacitor. So even a single shell can be treated as a capacitor, assuming the infinity is the second shell. And look at this thing, the interesting part. Now, if I try to find the energy for a single shell, what is the formula? Q square by 2C, which is Q square by 2 4 pi epsilon R. This is nothing but KQ square by 2R. This is again the self energy, remember? If you take a single shell, this is a self energy, isn't it? See, the self energy keeps popping up. It is the same thing. You can call it as a capacitor. You can call energy density. You can call it self energy. There are different names, but end of the day, they all mean the same thing. It's like if you have a monkey, right? You can call it bandar. You can call it different name, but yeah, end of the day, it's still a monkey. So something of that sort. You're just calling with different names. All clear with the stuff? A single shell and double shell. So these are new formula there. So till now, how many formulas you know? Q is equal to CV, field is equal to sigma by epsilon, or potential difference by distance. Uh, what is the other one? I forgot. C is equal to A epsilon by D for parallel plates. Force is equal to Q square by 2A epsilon for parallel plates. For spherical shells, there is no force. Energy is equal to half CV square, Q square by 2C. All that stuff. Energy density is half epsilon E square. For spherical capacitor, this capacitance ka formula will change. 4 pi epsilon R1 R2 R2 minus R1. The force is 0 for a spherical shell, because if you take concentric shells, the field inside the shell due to this guy is 0. So there will be no attraction. But Baki sub is valid. Everything else is valid. QCV, energy, everything is valid except force. All clear with this? Great. Now let me show you how they can ask some really good questions on this. So we have two shells. Radius R, radius 2R. Let's say this thing has a charge initially plus Q. This thing will have a charge 2Q. We have a switch here, and this is being grounded. If you remember, this is the Gauss-Log equation. Find the charge distribution and the heat produced when the switch is closed. If you remember, I taught you how to find heat produced also, but it was going very long. But this method I'll show you, will get it in pretty fast. Find the charge distribution and the heat produced when the switch is closed. Let's get this. These are some really good questions. Hope you guys remember the charge distribution. How do you handle this? Can you find a chart distribution that you can do, right? Okay. This is after grounding, right? Okay. Now, how do you think about energy? Okay, let's see. First, let's get the chart distribution. Now, when the switch was open, so let's say initially the switch is open. Now, what are the charges here? If this is Q, this will be minus Q. If this is minus Q, this will be 3Q. This is clear. This is when the switch was open. You need this. This is the scenario when the switch was open. So plus Q, minus Q, and 3Q. Okay. So this is the chart distribution. Now listen, this is the thing what I was saying. So if you look at the field lines here, so there are field lines here, and there are also field lines here. So can I say the space between R and 2R is one capacitor, that is C1. The space between 2R and infinity is the second capacitor. So C1 is the capacitance. So you can treat these spaces as capacitances. So this is a capacitance between R and 2R. C2 is a capacitance between 2R and infinity. What is the value of C1? Remember the formula, 4 pi epsilon R1 R2. So that is R2 by R2 minus R1, which comes out to be 4 pi epsilon R. What is C2? C2 is a single shell capacitance, which is 4 pi epsilon radius, which is 2R. This is 4 pi epsilon, 8 pi epsilon R. This is also 8 pi epsilon. So interestingly, both the capacitances are equal. You're getting it? So instead of finding self energy, interaction energy, and all that stuff we did, you can just treat that space as one capacitor. So what is the initial energy of the system? The initial energy of the system. So capacitor C1 has a charge Q, Q square by 2C1. The outside one is 3Q, so 3Q whole square by 2C2. This is the initial energy of the system. This includes self energy, interaction energy, all that energies that we did. If you remember in Gauss law, you can skip all that and you can say this is all the energy. Is this logic making sense? This is the key point here, that you can treat this as a capacitor and you can get all that energy stored. So when you say this U energy, this thing involves the self energies plus interaction energy. So all this is included in this. If you try to do it separately, you'll still get the same answer. And you know C1 and C2 ka value. Is this logic making sense? This is what makes this problems really good. You're introducing Gauss law, then you're introducing capacitance, and you're converting that into energy. This could be pretty good, what do you call matrix matching equations. Then now the switch is closed. Now when the switch is closed, what will be the charge distribution? What is the charge inside? I don't know because it is grounded. Charge is not conserved. This is minus q. This will be 2q plus q because outside is conserved. So let this point be A. Since you're grounded, potential at point A must be 0. What is the potential? Kq by small r plus k into 2q plus q minus q. That is the total charge on the outer shell by 2r is equal to 0. Small q will cancel. We get q is equal to minus q. That means the final distribution is looking like this. So if you don't know how to find this still is a mains question, remember the grounding part. So this is minus q, this is plus q, and this was plus q. This is the charges, everyone. And now, same story. This was capacitor C1, this is capacitor C2. What is U final? So the capacitor C1 has energy Q square by 2C1. The outside will be Q square by 2C2. So what is the heat produced? Initially, you had something which was more. Finally, you have less. So the difference must be the energy. You can clearly see Q square by 2C1, Q square by 2C1 will cancel. You are left with only the second term, that is 3Q square. So you want, I'll write down Q square by 2C1 plus 9Q square by 2C2 minus Q square by 2C1 plus 9 Q square by 2C2. Q square by 2C1 will cancel. That will be 9 minus 1, 8 by 2, 4. 4Q square by C2. But what is C2? C2 is 8 by epsilon R. So 4 and 2 will cancel. You end up with KQ square by 2R. That's your answer, everyone. Mm, I think my calculations are right, or I messed up the calculation. No, no, 2R nahi hai. 2 KQ square by R. Because that is 8 by 4 by 2. 8, 4 Q square by C, and C is how much? 8 by epsilon R. Okay, I want to write in terms of 2, right? Then it is fine. It's right. Are the steps clear, everyone? Oh yeah, where did you get that extra 4 you got, na, denominator mein? Check karo where you messed up. Did you use capacitors only? You tried self energy. Okay. This is a really good one. You should definitely have to handle this thing. You can see Gauss law, capacitor, we combine both. If you remember, if you try to use self energy and interaction energy, it will be a mess. All got this? How we did? I'll give you one more like this. You guys tell me how is the answer. Inner shell, outer shell. This time there's a switch between them. Nothing is grounded. This is R. This is 2R. Let's say this is plus Q. This is minus 2Q. Find the heat produced when switch is closed. If they just ask you distribution, it will be a good mains question. If they ask you heat produced, suddenly it goes to advanced question. Yeah, even under advanced, it is still moderate level equation. It's a good one. Find the heat produced when the switch is closed. Same story. First thing, you need to find the initial distribution, final distribution. Without charge distribution, you can't do anything. Then you know what to do. You treat them as two capacitors and finish it off. Okay, let's see. So step one, let's get the distribution first. So when the switch was open, what is the distribution? If this is plus Q, this is minus Q, and this is also minus Q. Agreed? This was capacitor C1, this was capacitor C2. Now, when you close the switch, now see, there is no need to solve anything. That's what I'm saying. If you actually remember, right, few things you can just see and guess. Listen to the logic here. Since you connected with a wire, this point and this point have same potential. Since the potential is same, there cannot be any field between them. If there's no field between them, that means this must be zero, this must be zero, this must be minus Q. Is that logic making sense? Think about this. If there is a charge here, then there will be field lines. If there are field lines, that means there is a potential difference. But since you connected them with a wire, there cannot be potential difference. So therefore, the inner shells will have zero charge. Do you guys remember that argument? I did explain you that in once, like without doing anything there. Now, observe karo, clearly observe karke dekho, you will notice something there. The C2 capacitor remained exactly the same, minus Q, minus Q. So outside, nothing happened. What changed was the field lines inside. So these field lines vanished. So outside, the field lines were unaffected. They were happy, normal, as usual. But the field here became zero. So from here, can I clearly say all the energy in the C1 capacitor became heat? The heat produced is nothing but energy stored in C1, which is Q square by 2C1. And what is C1? Q square by 2 into 8 pi epsilon R, which is KQ square by 4R. Making sense? How long it took actually to solve? It will take less than 2 minutes if you know your steps properly. So that is an idea. Meaning, yeah, agar ye click nahi hua 0 0, you know how to do. We will assume charge Q minus Q, Q plus Q. Then we'll say potential at A is equal to potential at B and do all that. So in case you're still worried, like how did I get this? We did this in Gauss law in the spherical things. This question, if you remember, page 84, kind of similar question. So, but you can actually find the charges here without anything with the statement. If there is a charge here, there will be field lines. If there are field lines, there will be a potential difference. But since you connected them with a wire, there cannot be potential difference. Therefore, there should be no charge. That's it. Ho gaya. There is no need to write any equation there. All got this? So there, Gauss law, capacitors. So it's a good combination of questions there. Any doubts on this? Clear? Next one. I'll give you one question as a homework. Try this and come. Next class, we'll discuss. I want you to spend some time on this. Let's say we have two hollow shells. This is R1. This is R2. I think this is from Erodo, I guess. I don't remember. It's a good one though. So hollow conducting shells, radius R1 and R2. This thing has a charge plus Q1. This thing has a charge plus Q2. The distance between them is L. And this L is much, much greater than R1 and R2. So the shells will think they are like point charges. Yeah. E1 bar is the field due to Q1. E2 bar is the field due to Q2 at any point in the space. Meaning, if you take any random point here, this guy will get a field E1 bar. This guy will give you a field E2 bar, something like this. You'll get a field like E1 bar and E2 bar. What I want you to find integral. So if you take the field at any point E1 bar, dot product E2 bar into dV. dV is the volume for the entire space. What is the value of this? dV is the volume, so for entire space. Now, meaning I'll tell you what I'm asking. So somewhere here you took a small volume. At this volume, you found the field E1. At this point, you found E2. Then you did the dot product, E1 bar dot E2 bar. That value into this volume will give you something. I want you to do this everywhere in the space from 0 to infinity. What will be that value? Right? So think about this. It looks weird. It looks like more mathematical, but there is a way to interpret this and get this. So spend some time, think about this. You will see an exact same question later on in magnetism. Usme I'll ask you a question. B1 bar dot B2 bar into dV, where B1, B2 are magnetic field due to wires. So story goes like that. So you will see a similar question later on. So there are two shells of radius R1, R2. E1 and E2 are the field in the space anywhere. You take the dot product of those two fields at that point and multiply with volume and integrate the whole space. And this quantity looks like completely nonsense, but it actually becomes something else if you can interpret it a certain way. Figure it out. You have time. Next class, I will discuss this. Starting of the class, just remind me if I forget. We will do this. It's a pretty good one. But are you clear with the question? What I'm asking? Yeah, great. So give it a try and see. If you have already seen this before, that is fine. It's still a good question. Next thing, we will see in the next class. Yeah, that's about a spherical capacitor. Not much. Next thing, cylindrical capacitor. How do you construct a cylindrical capacitor? We take long coaxial cylinders. We take a cylinder. We take one more cylinder. This is how you see most of the capacitors actually. If you see this picture, na, it's sub cylindrical capacitors. These are the actual ones. This is your R1, this is your R2, and this is your length L. Same story, we'll put a battery between them, voltage V, this will give you plus lambda, this will give you minus lambda, lambda is a unit charge. These are coaxial cylinders. We take L must be much greater than R1, R2 so that we can neglect the fringe effect. The field between the plates is given by 2k lambda by R. Hope you remember the field outside a shell, which looks like an infinite line charge where R is between R1 and R2. Same story, V plus minus V minus is equal to integral 2k lambda by R dr. Limits will go from R1 to R2. This will give you V is equal to 2k lambda ln R2 by R1. Lambda is nothing but Q by L. So if you do Q by V, C, that would be V is equal to 2k lambda is Q by L ln R2 by R1. So capacitance is Q by V. You can just simplify this. It ends up to be 2 pi epsilon L by ln R2 by R1. That's your result. This is the capacitance of a cylindrical capacitor. The formula is important. There is not much questions on this. Everything else is same. Energy stored Q square by 2C. Everything is same. This thing was asked in exams like anything. Bits or C mains made it was a direct question. They gave two cylinders and said find the capacitance. People didn't remember the result. And they do ask. Mains may last 5, 6 years if you see the paper. Out of 25 questions, there are at least 10 to 12 dumb questions like that. And even then, people do mess up and come. So you have to be careful. That's it. Cylindrical capacitor, there's not much. Like I said, parallel capacitor, there's a lot more. Spherical, we had little. Cylindrical, there's just a formula. Clear with this? There. So this is one part of the capacitors, right? We different types of capacitors and all that stuff. The second part, the most important thing, combination of capacitors. Whatever I teach you here, exact same thing we will use in current electricity. The concepts and everything will be same. But formula में there is a छोटा difference, but the ideas are the same. So listen carefully because what I'm teaching you now, I'm not going to teach you that again in current. They will do the problems directly. So combination of capacitors. So what happens if you have multiple capacitors together? And it's not like this is the first time. We already done things like this in heat transfer, conduction. We did this thing in Poiseuille's equation. Yeah, so we have done this kind of stuff before. Combination of capacitors. First thing, series. When do you say two capacitors are in series? They should have same charge and they should be in the same branch. So if you have two capacitors like this, now listen to this thing here. When you say a charge Q is coming to a capacitor, what is exactly happening? So when the charge Q comes from the left side, the charge plus Q will come here. And we know from Gauss law, if you have a plus Q, you will induce a minus Q on the opposite plate. Because you got a minus Q, the plus Q will go from here. So you'll get this plus Q here. This plus Q will induce a minus Q here. It gives you a feeling this Q will go away again here. So when you look at this scenario, right, it gives you a feeling as if the same charge Q is jumping over the plates and going, isn't it? But in reality, the charge will never cross this plate. If you look at this empty space in the middle, there is no connection between the plates. The charge will never jump from one plate to another plate. It is always inducing the charge and going away. Did you ever see a relay race? Imagine you have a 400 meters relay race played by four twins. We will not call them twins, we call them quadruplets or whatever. Now, how does it look like? So the guy one is running, he gives that baton, and the second guy runs. For a person who's seeing from far, it looks like the same guy is running, isn't it? It gives you something similar there. So this is the most important thing. Charge will never cross the plates. Charge will come and get stuck on the plate. It will induce a charge, but it gives you an illusion as if the same charge is going across the plates. Are you clear with this? So if this is C1, this is C2, and this is V1, and this is V2. So that is the first thing in charge distributions. The charge on the positive plate induces a negative charge on the facing plate, or induce an opposite charge. And because the charge has to be conserved, a plus Q charge will go ahead. So it gives you a feeling as if this plus Q has jumped the plate and went ahead. So it feels as if the charge is going across the plates. So be careful with that. The charge will never jump between the plates. Clear with this? So now what you want to do, you want to replace both these capacitors with a one single capacitor, C equivalent. Since the voltage is V1 and V2, its voltage will be V1 plus V2. That's your net voltage. V1 and V2. So this would be like V equivalent. Our voltage is across the capacitor. So V equivalent is nothing but V1 plus V2. But what is V? V is nothing but charge by potential difference. So remember, since they're in series, they'll have same charge, plus Q, minus Q. So you want to replace these two capacitors with one single capacitor with the same charge. So Q by C equivalent is equal to Q by C1 plus Q by C2 because they have same charge. So we get 1 by C equivalent is 1 by C1 plus C2. There. So the formulas are reverse of resistors. So capacitors will behave opposite to resistors. They behave like springs. If you remember, springs may be same formulas aaya tha. And the charge Q is given by C1 V1 is equal to C2 V2. So from here we can clearly see V1 by V2 will be in the ratio of opposite thing, C2 by C1. There, have a look at this. That's how you can derive this. So when you keep two capacitors in series, you can replace them with a single capacitor where 1 by C equivalent is 1 by C1 plus 1 by C2. This formula is reverse of resistors. All clear with this? So for the equivalent capacitor, the voltage adds up. Any doubts on this page? Next thing, parallel. When do you say two capacitors are in parallel? They should have same potential difference and across the same branch. Or same nodes, you can say. So same nodes. What is a node? For example, if you take a capacitor, the point where two branches meet is a node. Basically, the junctions. So node is simply the point where branches meet. What is a branch? The element between two nodes is a branch. So it's like, where is your house? Beside my neighbor ka house. Where is your neighbor ka house? Beside my house. So that's how it looks like. So the point where branches meet is a node. A branch is nothing but the element between two nodes. But anyways. So you have two capacitors C1 and C2. So let's say charge Q is going here. This is Q1 and this is Q2. You want to replace this with one single capacitor, C equivalent. So the total charge Q will be Q1 plus Q2. We are just using the same formula. What is Q equal to? Q is equal to CV. So Q is equal to C equivalent and V, C1V plus C2V because the voltage is same for all of them. Therefore, C equivalent is C1 plus C2. There again, reverse of resistors. So if you keep capacitors in parallel, they'll simply add up. So Q1 by Q2 is C1V by C2V. So the charge will divide in the ratio of capacitance. There, have a look at this. This is capacitors in parallel. All clear with this? The third one, Wheatstone bridge. This we have already done two times in heat transfer and Poiseuille's equation. So what's a Wheatstone bridge? If you have a capacitor, C1, C2, C3, C4, and C5. If C1 by C2 becomes equal to C3 by C4. And or you can write like this also, C1 by C3, C2 by C4, same thing. Then C5 can be removed. So your circuit becomes like this. Which becomes easy to solve. Now you can create an extended Wheatstone bridge. Suppose if you have a scenario like this, C1, C2, C3, C4, C5, C6, C7, C8. If C1 by C4 becomes equal to C2 by C5 becomes equal to C3 by C6, all three should satisfy. Then you can remove C7 and C8. Even if one of them doesn't satisfy, let's say these two will work, but this does not work, then the whole thing goes off. Circuit the symmetry, it will lose its symmetry. So this is called an extended Wheatstone bridge. You can do this even if you have multiple things. Easy to prove, na? Think of like this. If C8 and C7 are not there, now because the ratio is same, so this point and this point will have same potential as this point and this point, isn't it? Up and down will have identical potentials. If you keep a capacitor between two same potentials, what will happen? Charge will not flow. Potential difference is zero. Making sense? मतलब देखो logic ये था. Suppose if you have a capacitor, let's say this is 2 farad and 4 farad. If you take another capacitor, let's say this is 3 farad and 6 farad. Now, forget about this thing. If you just look at here, because this is 2 and 4, the potential here, because this is 3 and 6, 1 is to 2, this also will be V, right? The potential will divide in the same ratio. So if you keep anything between them, since the potential is same, charge will not flow. Got the idea? So it's because the potential will drop in the ratio. Exact values, we don't care. All clear with this? Great. So you got series and parallel. Let's do one question on this. So let's say we got a battery, V, capacitor, 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 capacitor. This is a conducting wire. This is C, this is C, this is C, this is 2C, this is C, and this is C. Find C equivalent and find charge on the capacitor. And charge on each capacitor. What does that wire do exactly? If one of the ratio is not same, then you cannot remove the capacitor. That's it. So no, because the ratio is same, you can remove. If it is not same, then you can't solve the question. It becomes we have to use some other method. Think for a minute. I'll tell you what happens with that wire. You know by now, right? What happens? What does a wire do? If you put a wire, it will make the potential same on both the sides. That's it. That's what it does. Don't say like capacitor ud jayega, it will blast. All nothing. It simply means the potential on both the sides will become same. Formulas. Which formulas you want? God. क्या था सीरीज में 1/C equivalent is 1/C1 plus C2 reverse of resistors parallel में C1 plus C2. Okay, let's see. So first of all, let's talk about what happens if you put a wire. This is important. A conducting wire has only one thing. It will make the potential same. बस और कुछ नहीं करेगा. A conducting wire makes the potential same for the connecting nodes. So whichever points you connected, दोनों का potential same हो जाएगा. Okay. So now if you take a capacitor and if you connect a wire, this point A, this point also becomes A. That's what it does. This phenomena is called shorting. If you put a wire across a device, it is called shorting. We'll say it got shorted. So shorting means wire across an element. Then we will say, since the potential difference is becoming zero, there is no potential difference across the capacitor. Q is equal to zero. Therefore, the capacitor can be removed. It is useless. Clear? Now, be careful. Huh? You can't do this every time. For example, देखो अगर capacitors are like this, and now if you put a wire across this, do you think you can remove these two? You can't remove these two because see, this is A, but this will be some other point, isn't it? Every node will have different voltage, so you can't remove them. So be careful with that. Just because you put a wire doesn't mean you can remove it. So yeah, that's the main idea there when you put a wire across an element. So then you can remove this capacitor here. So this is useless. This is how the circuit looks. This one, the three red ones will be in series. The two green ones will be in parallel. So how will the circuit look? If you are in series, the capacitance will be what? 1 by C plus 1 by C. So this will become C by 3. If you are in parallel, they will simply add up. This will become 3C. So this whole circuit can be simplified like this. And these two are in series again. So formula is C1, C2 by C1 plus C2. That would be C by 3 into 3C by C by 3 plus 3C. That would be 3C by 10. That's your C equivalent. So what is the charge? Q is equal to C equivalent into V. So the charge flowing through the battery is 3CV by 10. So this much charge will go through the battery. Now look at this thing, charge distribution. So if Q goes from the battery, this capacitor will get Q, this capacitor will get Q. So this Q is continuously flowing. Now, if they're in parallel, the charge will divide in the ratio of opposite. Q is equal to CV. So Q is proportional to C. So this will be Q by 3. This will be 2Q by 3. So more capacitance, more charge. And again, Q will come out. This will be Q. And again, Q will come back. So remember, if Q goes out from the battery, Q has to come back to the battery. This charge distribution is clear, everyone. Whoever are in series, they'll all have same charge. If you are in parallel, it will split in the ratio of C1 is to C2. Any doubt on the distribution? Yeah, most of you did get the C equivalent part, but clear with this? Take a break. Come back by 9:45. We'll continue from here. Any doubts on this? Anyone not sure? You can ask me. Or go take a break. Come back in by 9:45. Chalo, come back by 9:45. Chalo, let's see one more. So when you solve circuits, right, in total there are like five techniques you can say. One is series parallel, Wheatstone bridge, nodal analysis, symmetry. The symmetry is a big one. Even in that, you have multiple sections. And the last one is your Kirchhoff's junction law and loop law. The fifth one is the final weapon. Like everything works, but sometimes it becomes really lengthy. So these five techniques you can solve literally any type of circuit. So currently we are playing with series and parallel. So let's say we have four capacitors with a switch between them. This is C, this is 2C, this is 2C, this is C. Be careful, this is not Wheatstone bridge. बीच में कैपेसिटर नहीं है. This is voltage V. This is your switch. First question, find C equivalent before and after closing the switch. So if you close the switch and open the switch, the whole circuit changes. How much charge flows through the switch when it is closed? So when you close the switch, some charge will go through it. That would be a good one. Find the heat produced when switch is closed. Let's get the first one. Okay, let's see. Yeah, C equivalent, I think most of you got it. Okay, let's see. So when the switch is open, how does the circuit look like? This is a open switch. This is closed. So this is easy to see. These two are in series, right? So these two are in series. How much is this? C and 2C. So that would be 2C into C by 2C plus C. 2C by 3, 2C by 3. So these two are in series. 2C by 3. These two are in series. 2C by 3. So we get C equivalent is equal to 4C by 3. These two are in parallel. You can add it up. What about this guy? This one, what you can do, you can modify it a bit. We'll do one thing here. Let's do for the open part only. Okay. We got C equivalent is 4C by 3. So from here we get charge Q is equal to 4CV by 3. Now how will the charge distribute? Look at the charge distribution. So whatever charge will come from here, 4CV by 3, because the upper one is 2C by 3, bottom is also 2C by 3, it will split equally. So whatever charge you're sending, 4CV by 3, it will split equally 2CV by 3 and 2CV by 3. The distribution is important. So this is how the charges will look, everyone. So on this left plate, we'll have 2C by 3. It will induce a negative charge on the other plate. I'm marking with green 2CV by 3. This plate will have 2CV by 3. This plate will have minus 2CV by 3. Okay? We just need that. You will understand why. So I'm marking these plates in black, okay? So keep these black plates in mind. Clear with this? So this is the scenario when the switch was open. Any doubts on this part? Now, you close the switch. When the switch is closed, now this thing, when you see this, some people can figure it out, oh, yeah, parallel, hai, but sometimes it doesn't click. So can I redraw the circuit like this? Because that switch is closed, I can just compress the wire. So this wire, I can compress it. And can I just draw it like this? Do you guys agree both are still the same? So what I did was this entire wire in the middle, I made it like this. Do you guys agree with this? So that entire wire in the middle, it becomes like this. This is C, this is 2C, this is 2C, and this is C. Now see what happened. These two are in parallel, which is 3C. These two are in parallel. This became 3C. Therefore, C equivalent will be 3C by 2. See, the whole answer changed. So what is the charge here? 3CV by 2. Is this making sense? How will the charges distribute? Again, same story. So if you look at the charge distribution, so from here we'll get 3CV by 2. Now because that is C and this is 2C, charges will split in what ratio? C1 is to C2. So the charge will split here CV by 2 and charge will split here CV. So this plate will have minus CV by 2. Maybe I'll draw one more picture. Wait, that looks confusing. This is how the charges will distribute. So this is 3CV by 2. This side you will get CV by 2. This side you will get CV. So this plate will have charge CV by 2. And this plate will have charge minus CV by 2. Similarly, this guy will get charge CV and this guy will get minus CV. The charge will again flip. Is that making sense? Because now this is 2C and this is 2C, isn't it? So here you will get CV by 2. Here you will get CV. यहाँ से वापस 3CV by 2 जाएगा. This guy will go CV and this guy will be CV by 2. It will flip. Now, why you need this? You will understand. See. Now again, look at the same two black plates. Let's look at the picture. You will notice the difference now. So whenever they ask you find the charge through the switch, this is how you proceed. Observe these black plates. Previously, this thing had a charge of minus CV by 2. This thing had a charge of CV by 2. Now here, after closing the switch, this thing has a charge of minus CV by CV by 2. No, wait, that is 2 CV by 3. My mistake. Minus 2 CV by 3. This was 2 CV by 3. Now this thing had a charge of minus CV by 2 and plus CV. Now look at the argument here. Initially, how much charge was there in both the plates? The charge on the black plates initially was 0. Now what was the charge on the black plates? CV by 2. Where did you get this extra charge from? The only way these two plates can get any charge is through the switch, isn't it? The two plates are isolated. They cannot get charge from anywhere else. The charge has to come from the switch only. So if you observe these black plates, the initial charge was 0. Plus 2, minus 2 CV by 3 and final 2 plus 2 CV by 3. The final charge was CV by 2. So this additional charge must have come through the switch. So therefore, the charge CV by 2 must have flowed through the switch. That's it. There is no other way to get a charge. All clear with this? Any doubts on this? Clear? Everyone got the equivalent part? And everyone understood how to figure out the charge part, right? Question still not over. We have to find the heat produced. How do you do that? Now it is manageable. Look at this thing. So initially, how much charge was going? 3 CV by 2. Now how much charge was going? 4 CV reverse. 3 CV by 2 and 4 CV by 3. Okay. So what is the initial energy? U initial is half C equivalent into V square. What is the C equivalent initially? 4C by 3. What is C equivalent finally? 3C by 2. So you can directly get the energy from here. Half 4C by 3 V square. What is the final energy in the system? Half 3C by 2 V square. Great. What is work done by the battery? Now this is important. So work done by the battery is the charge flown through the battery into voltage of the battery. Now, so if the voltage is V and if the charge comes out of the battery, then the work done by the battery is plus QV because the battery is discharging. This is what happens when you use your mobile phone. The battery is discharging. So work done by battery is positive. Suppose if you send charge into the battery, this is what happens when you charge your mobile phone. If you charge into this thing, the battery is getting charged. So in this case, battery does not do work. Battery, absorbs work. So work done by battery is negative. So it is important to see whether the charge is going into the battery or coming out of the battery. Clear with this? So now in our question, look at here. Initially, how much charge went? 4 CV by 3. Now how much charge went? 3 CV by T. So what is the difference in charge? So that extra charge, when you close the switch, the extra charge that went from the battery is 3C by 2 minus 4 CV by 3. That would be 9 minus 8, so CV by 6. So this is the extra charge. So what is the work done by the battery? The charge, that is CV by 6 into V. That is CV square by 6. Great. Then how to get the heat produced? You know the formula. Heat produced is your initial energy plus work done by battery minus U final. Substitute the values, you'll get the answer. If you do this, how much you'll get? You'll get something. Check it out. Is this clear, everyone? You have to include work done by battery. Most people forget that. If you just take U initial and U final, you won't get anything. Okay, people are saying this is CV square by 12. So please verify your answer. Is this clear, everyone? The question looks very innocent, but you can see how many things are there. Just closing the switch can create this many problems. If this was a simple mains level question, they would ask you find C equivalent before and after. They want to torture you a bit. They will ask you find charge flown through the switch. If they ask you heat produced, it'll still be an advanced question, but advanced may it'll be easy to moderate level things. That's, yeah, you have to do little work, but it's a good one. All clear with this? Any doubts on this? Clear? Great. I know this is a little lengthy, but let's see. Next one is a good one. Now the remaining circuits will look a little interesting. So we have 3 capacitors. You connected a wire here, you connected a wire here. Capacitance is C, capacitance is C, capacitance is C. So I'm not going to put a battery anymore. So A and B. So these are the terminals. So they'll simply ask you like this, find the capacitance between A and B. The meaning of this is you're going to connect the battery between A and B. So if you put the battery between A and B, what is the equivalent capacitor? How will you do this? And you look at this, it gives you a feeling, oh, it is looking like something, but it looks weird also. This is our second method, everyone, nodal analysis. So listen, I'll show you the steps. You can call it anything on nodal analysis, node method, number method. People have different names for this. So in this, step 1, locate the different number of nodes. So everywhere there's a branch meeting, that is a node. Identify the number of nodes and check for nodes with same potential. See if any nodes have same potential. Step 2, name the nodes. If 2 nodes have same potential, call them with the same alphabet. You can call them A, B, C, D, 1, 2, 3, whatever you want to call. Step 3, redraw the circuit. Okay, so listen to this, everyone. So step one, locate the nodes. So this is A. Now remember, this is a wire, isn't it? If you keep a wire, the whole wire becomes A. So if this is A, this is also A. Do you agree? That's what a wire does, right? It makes the potential same everywhere. If you call this B, then this whole wire also becomes B, green one. So how many nodes are there? We have node 1, node 2, node 3, node 4. But how many different nodes are there? There are only two different nodes. Making sense? Even though there are four nodes, in reality, there's only two nodes, A and B. Redraw the circuit. So let it be A and let it be B. Remember, always keep A and B in the edges. Now, for convenience, let's number the capacitors. Let's call this capacitor 1, capacitor 2, capacitor 3. Look at this. Capacitor 1 is between which two nodes? Capacitor 1 is between A and B. Capacitor 2 is between A and B. Capacitor 3 is also between A and B. Now, can you see the circuit, how it looks? If you redraw the circuit, it becomes like this. All three capacitors are in parallel. Therefore, C equivalent is equal to 3C. Do you guys get the logic? If you connect 2 points with a wire, potential is same. If you don't connect, then the potential is not same. Then you use a different alphabet. Then get these alphabets, redraw the circuit, put the capacitors back. Got a rough idea what is happening? Let's do one more. You'll get the hang of it. You guys give it a try for this. All are same capacitance, C and C and C. Let's get this thing. Find C equivalent. All capacitors are C. Yeah, logic is fine, but things get complicated, you won't understand. Remember, step one, locate the number of nodes. How many nodes are there? 1, 2, 3, 4. Step two, see how many nodes are identical. Since this is A, this entire wire will have same potential A. So this point also must be A. Next thing, this is B, but there is a capacitor here. So I don't know what is that. So this is some point C. Got it? So if you have a capacitor, then it is not B, it is something else. I don't know what it is something else. Done. So we have 3 points here. So A, C, and B. Remember, A and B should be always on the corners because that is where the battery is. Okay, let's number the capacitors. Let this be capacitor 1, capacitor 2, capacitor 3, capacitor 4. Where is capacitor 1? Between A and C. So draw 1 here. Where is capacitor 2? Between A and C. Where is capacitor 3? Between A and B. Where is capacitor 4? Between B and C. Can you see this series parallel? These two are in series. This and this are in parallel. This thing and the bottom one are in parallel. Please have a look at this. So how much is this capacitance? So this is C and C will be 2C. So this combination will be 2C. 2C and C will be 2C by 3. 2C by 3 and C will be C equivalent, which is 5C by 3. Any doubts on the B part? Please ask me. Yeah, right, Utsa. Right, Samya. Any doubts on the B part? These are important ones. Please ask me if you're confused because exact same thing you will learn in current electricity. Instead of capacitor, you'll put a resistor. Idea is exactly same. What about the third one? Look at this. This is point A. So TK, that is A. This is B. So that is B. Fine, fair enough. But if you look at this entire circle outside, this entire circle is a conducting wire, meaning this is potential C. This is also C. This is also C. This is also C. That's it. There are only three nodes again. So A, C, and B. Let's number the capacitors. Capacitor 1, capacitor 2, capacitor 3, and capacitor 4. 1 is between A and C. 2 is between A and C. 3 is between A and C. 4 is between B and C. देखा circuit कैसा हो गया? Once you redraw, things will become pretty simplified. I hope you're able to see that simplification. Then you're done, right? All these three are in parallel. So that would be 3C. This would be C, and both are in series. So 3C, 3C by 4. Is this clear, everyone? Did everyone got the idea there? How do you know you have to use this? Even, the moment you see a conducting wire, the potential becomes same. The moment you see one or 2 points of same potential, you can simplify the circuit. So that is a major thing. The advantage of this method, right? It will decrease the number of nodes. If you decrease the number of nodes, the circuit becomes simplified. All clear with this? Let's see one more. Now you guys give it a try. If you got this, I think then you understood. Yeah, it'll take a little more time to understand how to draw and all. And one more thing, when you're drawing A, C, B, whatever, make sure, never draw things like this. Don't cross like this. Don't cross wires like this. If you cross wires like this, again, you'll get confused. So draw them in such a way you are not crossing. Meaning, देखो how I'm drawing. They're not crossing each other. Clearly, दिख रहे who is series and who is parallel. Yeah, that is not a concept, but yeah, just an idea there. These 2 points are connected with the wire, everyone. C, 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 and C. The battery is between A and battery is between B. Find C equivalent. This thing is a conducting wire. The left one, this wire is a conducting wire. That's what the moment you see a wire like that, it is understood. A point or A point potential same. And if 2 points have same potential, nodal analysis is the way. That is how you get an idea. Okay, I think nodal analysis will work here because you can decrease one node, so circuit can become simplified. Hmm, 13 by 8. Right, Param. Right, Samya. Right, Shan. Shman. How do we start? Step 1, find the nodes. If this is A, this entire wire also is A. So this is also A. This point is not connected to anyone. So let it be C. This point is also not connected to anyone. So let it be D. So if it's not connected to anyone, it's a different alphabet. That's it. So there are 4 points. So let's draw them. Remember, A and B should be always in the corner. C is next, D is next. Because when you go from A to B, you're getting C and then you're getting D. So try to follow that order. Let's number the resist capacitors. Let this guy be 1, 2, 3, 4, 5, and 6. So 1 is between A and C. 2 is also between A and C. 3 is between A and D. 4 is between C and D. 5 is between D and C. D and B. 6 is between, again, these two. There you can clearly see here how it is. Okay, so these two are in parallel, these two are in series. Then this upper one and the bottom one are in parallel. Again, this left and this thing are in series. And again, parallel. So series, parallel, everything goes off. You get 13C by 8. You can verify your answer. Are you guys able to see that circuit, right? Why it is series and parallel? I'm putting curvy wires. If you want, you can put straight wires and draw the same thing. If you want, I can show you one. It would look like this. You get this, and then one more like this, and then you're putting one more like this. Yeah, same thing. When if you put straight wires, it will look like this. So series parallel, you can solve. All clear with this. Let's see one more. I am keeping all this at one place. Let's say we have 5 parallel plates. Parallel plates, area A, distance between them is D. You connected this wire and this wire. And you connected a battery between this guy and this guy. Hmm. Hmm. Find C equivalent. Now, before starting the question, can someone tell me how many capacitors are there here? Ask yourself, what is a capacitor? The space between the plates. So this is one capacitor, second capacitor, third capacitor, 4 capacitors. There are 4 capacitors. Hope you realized it. Yeah. Now go ahead. Each plate is not a capacitor. The space between two plates is a capacitor. So there are 4 spaces. We don't consider the outside ones. Those are useless. Because in a parallel plate, the outsides will not have any charge, so they won't matter. Get this? Let's see how will you do this. It is the same thing, nodal analysis, but yeah, a little different. Step 1, identify how many nodes are there. Step 2, see if there are any common nodes. Step 3, redraw the circuit, and you're done. Once you redraw, most of the times you'll get a simplified circuit. Let's get this. Let's get this. Solve this. Find C equivalent, everyone. Chalo, chalo, Srihari, get the capacitance. Find C equivalent. Hmm, 2A epsilon, 2A epsilon, yeah. 2 by 3, you're getting most of you. Others, answers. And others, do keep your cams on. Arya, Ishman, Ovia, cams on. Okay, let's see. So for simplicity, first let's define something. C is equal to A epsilon by D. Okay. Great. Next thing, let's call this point A. Let's call this thing point B. Let's call this thing point C. Let's call this point D. If this is D, this also has to be D because both are connected by a wire. That's the main idea there. You connect something with a wire, the potential becomes same. Great. So where is the battery? Battery is between A and B. Always A and B should be in the corner. Remaining all will be in the center. So C and D. Okay, let's draw them. So this is one capacitor, this is the second capacitor, third, and this is fourth. So where is capacitor 1? It is between A and D. So it will look like this. Where is capacitor 2? It is between A and C. Where is capacitor 3? It is between C and D. Where is capacitor 4? It is between D and B. There, this is the circuit, isn't it? Looks easy. So if you redraw this, it looks like this. So that is the advantage. You can see, right? The circuit becomes so simple to solve. Abhi dikh raha hai clearly. These two are in series. These two are in parallel, and that and this are in series. So how much will that be? This will be C by 2. That will be C, 3C by 2, 3C by 2 into C by. You're getting 3 by 5, right? You're getting C equivalent is 3C by 5. Yeah, right, Samyak. So check people who got 2 by 3. Someone got 0 also. Interesting. So see, these two are C and C, C by 2. C by 2 and C are in parallel. So 3C by 2. 3C by 2, C are in series. So C1, C2 by C1 plus C2. Be careful. Series parallel, I think some of you are mixing up the formulas. All clear with this. I hope you're getting how to use this nodal analysis thing. Any doubts? Great. Let's go ahead. Let's see something else. All are C. Find CAB. Look at this circuit in the middle. Huh? I did this curve, isn't it? So the curve meaning it is jumping over the wire. They're not touching each other. Find C equivalent. Right, Samya. Get this thing. Let's see how you handle this. Okay, let's see now. First thing, see. When you see something like this, you'll get a feeling, oh, nodal analysis use karte. See what will happen. I'll tell you when to use, when not to use. This will make things clear. Okay, you will say, okay, this is A. Oh, there is no wire, so this is not A. This is something else. This is B. Oh, there's no wire, so this is D. So how many nodes are there? One, two, three, four. How many different nodes are there? Four. Matlab, there's not even one node which is same, isn't it? So if you try to redraw the circuit, you're not going to get anything new. So remember this one thing. Nodal analysis is useful when at least you have one common node. It will make your life simple by eliminating, by making the circuit simpler. But if you cannot eliminate any nodes, the number of nodes are equal to number of unique nodes, then nodal analysis is useless. It will be of no use, right? So then how do we do this? If you see carefully, right, it's a hidden Wheatstone bridge, if you have noticed it. See, if this is A and B, let's not use nodal analysis, it won't work, but you will see something. This is C and this is D. I don't know whether you could see this or not. If I remove this in the middle, can you see it's a Wheatstone bridge? This by this is equal to this by this. If you see, it is actually a little crooked. If you can see it now, but let me redraw it for you. So A, C, D, and B. I'll draw it like this. Now you'll observe. Let this be 1, let this be 2, let this be 3, let this be 4, and let this be 5. So 1 is between A and C. 2 is between C and D. 3 is between D and B. 4 is between A and D. 5 is between this. This is a hidden Wheatstone bridge. Did you see this? So थोड़ा wires को twist करेंगे तो you will see it's a Wheatstone bridge. And then you know what happens. So this is a Wheatstone. You can simplify this like this. So C equal and CAB will be C only. That's it. So that's your answer. Can you try for B also now? B is also a Wheatstone bridge. You just need to figure out how. Think, I'll give you a minute. If you redraw, you will see it's also a Wheatstone. This is your third one, everyone. Wheatstone bridges. Mm, right, Arya. नहीं उत्साह. Second one is wrong. Aditi, you're right. Again, name them. So this guy is A, this guy is B, this is C, and this is D. That is the biggest clue. None of the nodes are same. So using nodal analysis is useless. Let's put the points again. A, C, B, D, and B. If you redraw this, this is how you will see the circuit. You will see one more capacitor parallel to the Wheatstone bridge. So this is a Wheatstone bridge with a capacitor in parallel. This is how the circuit looks. So this is also a Wheatstone. So someone took a Wheatstone bridge and kept one more capacitor in parallel. So CAB will be 2C. Okay with this? The middle one can be removed again. So upper wale will become C. C and C are in parallel, we get 2C. Any doubts on this? This is the third one, the Wheatstone bridge. The fourth technique is symmetries, but in symmetries, there are a lot of symmetries, which we will do in more detail in the next class, but let's do one problem now. An infinite ladder. So this is C, this is 2C, this is C, this is 2C, this is C, this is 2C, and so on. So the battery is going to be connected between these two terminals A and B. Find CAB. This is an infinite ladder. You're just adding C to C, C to C, and so on. What is the equivalent of this? If you connect a battery between A and B, if you replace this entire thing with one single capacitor, what is the value? So in symmetries, we have infinite ladders. This is an infinite ladder. Then we have infinite grid. Then we have axial symmetry, bisector symmetry, diagonal symmetry, cube symmetry. So there are a lot of things. So next class will be quite important in that sense. We will do a lot more circuits. And these are actually kind of fun. And everything you're learning, exact same thing you can do in current, replace resistor with a capacitor with a resistor, you get the same stuff. Okay, let's see. Most of you got it, I guess. C by 2 plus or minus root 3 minus 1. Okay. Now, how to do these kind of questions? This is not the first time you're seeing this. This question, right, is actually inspired from the max question, if you remember. Y is equal to root over 2 plus root over 2 plus root over 2 plus. Yeah, the question. How do you do this kind of a question? You will say, since it is going to infinity, the whole thing is y. So this will be y is equal to root over 2 plus y. Remember this logic? Then you square on both sides, you get a quadratic and you solve. And you have seen this before. You've seen this thing in laws of motion, if anyone remembers. Hmm, this one, infinite pulleys, yeah? We did the same logic. We said let the whole thing be x, and then we said replace with an x. We actually did this problem based on resistors. Great. So then how do we do this thing? So let's say the whole answer, right? Let CAB be equal to x. Let CAB be equal to x. Now the logic is if you cut one branch from here, this whole thing will still look same as an infinite branch, isn't it? So after one branch, this whole thing is still infinity. So this whole thing looks similar to the whole circuit. Looks similar to CAB. So that means this can be replaced. So you can replace this whole thing with another x. Making sense? Infinity minus 1 is still infinity. So this is C and this is 2C. So what is this equivalent? So this equivalent CAB, 2C and x are in parallel, 2C plus x. 2C plus x and C are in series, so 2C plus x by 2C plus x plus C. But this is nothing but equal to x. You get a quadratic equation. 2C square plus Cx is equal to 3Cx plus x square. We get x square plus 2Cx minus 2C square is equal to 0. Get the roots from here. So x is equal to minus 2c plus root over b square. That will be 4c square minus 8, I think 12c square by 2 minus 1 plus root 3c. That's your answer, everyone. Root 3 minus 1 into c. Are you clear how we handle an infinite ladder? You will say the whole thing is x. Leave one branch, then the remaining is also x. Put that back x, and you say if this equivalent must be again x. I hope the story was clear. Infinite ladders. This is a technique you use for infinite ladders, and this comes from a max problem. This one. This is actually inspired from a max problem. So there. All clear with this? There. So that is one other thing. So next class when you catch up, we'll do more from here. So please make sure to go through the notes. Like I'm saying, you can do finish your Gauss law and everything backlog. After next class, you can start doing capacitors. You'll be able to handle most of the questions. So, but next class will be quite important. We are going to do a lot of symmetries. We'll see more types of circuits. Okay, with that, we'll wrap up for the day. And do remember, there's a test online till tomorrow. So make sure to give it. And Saturday, there is a, the favor party for your seniors. If you can all come, it'll be great.